Hello, my name is Marcus Collier-Wright. I'm co-founder and CTO of Neutron Star Systems, and I'm very happy to be here today to be telling you about our overview of NEP, that is nuclear electric propulsion, for human space exploration missions to Mars. So to begin with, I'm going to be briefly talking about why we need high power for space, how it has an important role to play for ambitious missions like Mars missions, and how high power can enable new capabilities. I'll then talk a little bit about nuclear as a power source, and again, its relation to space, what kind of options we have available when we look at nuclear power for space, and what is the current status quo of these options. I'll introduce superconductor technology as a key element of the high power question and the role that they have to play on various space applications. I will then also talk about the various electric propulsion options which we have for nuclear power, and talk about which ones could be a good fit for these high power applications. I'll finish up with giving an overview of various nuclear and nuclear electric programs for space that are currently underway across the world, and then wrap up with some key conclusions from the talk. So in order to understand the need for high power, first we need to understand the fundamentals of electric propulsion. Now, electric propulsion is used in orbit to propel satellites as an alternative to chemical propulsion. Now, chemical propulsion is simply limited by the available energy within your fuel, but with electric propulsion, we are only limited by the power availability, and a number of technologies exist for this to turn power into thrust, usually by means of some kind of plasma phenomena or some kind of electromagnetic or electrostatic acceleration. Now, what is interesting to note on this slide, which shows a number of different propulsion technologies such as Hall effect thrusters or grid iron thrusters, is that we typically have a trade-off of our two axes. In this case, our two axes are thrust on the y-axis and specific impulse on the x-axis. So typically, if we want to have higher specific impulse operation, which is of course attractive because then we need less fuel to perform our orbital transfers, then we're going to have a penalty of a lower thrust. Now, low thrust is characteristic of pretty much every electric propulsion system, so typically this penalty might not be too bad. However, we also need to consider that when we look at really ambitious missions like going to Mars, especially sending humans to Mars, then we're going to be dealing with very large spacecraft which are capable of carrying the crew, the astronauts, and all the various life support that they need for their journey. So what we need to do is to be able to operate at a high specific impulse in order to minimize still the fuel consumption, but also at a high thrust in order to make sure that this journey does not take an unreasonable amount of time. And that's where it's important now to realize that on the y-axis we don't talk just about thrust, but thrust per power. So for every extra amount of power that we can provide to a system, we can increase the amount of thrust. And there, the case for high power is already made, because if we want to have high specific impulse and high thrust, then the only option is going to be to have a high power which allows us to achieve the thrust levels we need also at the relevant specific impulse. So coming now to nuclear as a power source and what role that has to play for achieving high power. Well, let's start off with the fact that nuclear is not completely new in space. It's been used previously on a number of spacecraft in the form of radioisotope thermoelectric generators. These have been used on some deep space missions like the Voyager probes, where the distance at which they traveled was too far away for solar panels to be technically suitable. And these essentially use a decaying isotope, a radioactive one, to generate heat, which is converted then into electrical energy. Now, these have a significant space heritage. However, their power generation is limited only to a few hundreds of watts, which is not really anything groundbreaking, especially when we look at today's solar power technologies. The next option for nuclear is fission reactors, of course widespread now around the world in energy generation needs. Fission reactors can generate significant amounts of power also in a quite compact space. A number of different projects have already been proposed, with a couple of experimental reactors flown in space by the Soviets several decades ago. And in this picture we have, for example, the Kilo Power project from NASA, which was aiming to test a fission reactor on the kilowatt scale. The benefit of these fission reactors is that they are in principle quite scalable, anywhere from kilowatt up to megawatt level, which means that they could also be utilizing the same basic technology for near-term demonstrations and early applications, whilst also laying the groundwork then to be able to scale up to the megawatt level as might be needed for human missions to Mars. The third category of nuclear we could consider is for fusion reactors. Now, these have a lot of benefits, mainly in terms of the fact that they are energy positive, so we actually get more energy out of them than we put in. Having said that, they are notoriously difficult to design. This has been an effort around the world for several decades already. There's a number of projects trying to get them working in a terrestrial environment, and these still have some way to go. Nonetheless, this could be an option for some far future applications. And here, with the fusion reactors, we have a scalability question where potentially they will be more scalable to higher power classes than fission reactors, also with a more power dense arrangement. However, as mentioned, this will take some time still to become a reality. So at this point in time, we need to focus mainly on fission reactors as the next development and area of focus for nuclear power in space. So we have our high power energy source. Now we need a way to be able to manage and process this power. And this is where high temperature superconductors come in. A superconductor is any material which can conduct electrical energy or electricity with zero resistance. And these superconductors only exhibit superconductivity when they've been cooled down to a certain temperature, below the critical temperature, which is the point at which superconductivity starts to be exhibited. Now, the first superconductor was discovered over 100 years ago with very low critical temperature of only a few Kelvin. And following that, over several decades, the temperature of superconductors was gradually increased with the discovery of new materials. But it wasn't until the 1980s when there was a significant leap forward with the discovery of several copper oxides, which were termed high temperature superconductors. And these were able to achieve superconductivity at much higher temperatures on the order of 80, 90, even 100 Kelvin. So what this meant was that we could achieve superconductivity with much less cooling required, which drastically changed the question for the cryogenic systems that were needed to implement superconductivity. Over the last 40 years, this technology has been maturated significantly and is now available in commercially off-the-shelf multi-layered tapes, like you see in this picture on the right. These tapes are formed of a number of material layers, with the superconductor layer itself being only a few microns thick, but they are produced with a very modular and high-quality production process, which has enabled cost-efficient production to be reached. This is thanks to the scalability and modularity of the process, as well as the implementation of industrial standards and the fact that several robust processes are used, meaning that we have a high yield of tape. When we combine all of these things together, what we end up with is now a very established industry of manufacturing of superconductor tapes, which are produced in a high quality at economies of scale on the order of several hundreds of kilometers per year. And these suppliers can be found all over the world, in China, in Japan, in Germany, and in the United States, just to name a few countries. Thanks also to these economies of scale, these tapes can be procured now at very reasonable prices. And this, in combination with their high temperature of superconductivity and therefore low cryocooling power, makes them very well suited for space applications. There are a number of different space applications that we could consider with the use of superconductors. In general, any application where we need a decent amount of current, including things like power transmission lines, could benefit from the use of superconductors through an elimination of ohmic heating losses and also reduction in mass and volume. The other category that we consider is for applications which require high field strengths, for example, in electric propulsion, in re-entry shielding or electromagnetic shielding, where the use of superconductors enables the production of very lightweight and compact coils for generating high magnetic field strengths on the order of several Tesla. One such application for this is the applied field magnetoplasmadynamic thruster, which is a type of electromagnetic propulsion system. The thruster is formed of two electrodes which are electrically insulated and between which we feed a electrical voltage generating an electric field. We feed a propellant into this field as a gas, and here it is ionized, forming a plasma. The plasma conducts a resulting current arc between the cathode and the anode, and as a result we have a self-induced magnetic field forming. The interaction of these electric and magnetic fields therefore leads to an electromagnetic acceleration through the Lorentz force, and this is the most basic force of the magnetoplasmadynamic thruster. Now this is known as a cell field thruster in this configuration where we only have this one acceleration mechanism. However, this is only suitable for extremely high powers and high currents, which means that in near-term applications it can't be used. The solution to this is to extend the physics of this thruster by adding an applied field coil. Here we use an electromagnetic coil or a permanent magnet to generate an axial magnetic field, which then leads to the formation of two further acceleration mechanisms, known as the Hall and the swirl acceleration. Now, the combination of these various acceleration mechanisms, as well as some of the other characteristics of the thruster, lend itself to have a number of benefits over existing technologies. The first is a wide propellant flexibility, meaning it can operate on cheap propellants, which are over 100 times cheaper than those used by competing technologies. The second is that thanks to the fact that the entire plasma is accelerated, we don't need an external neutralizer like in Hall effect or gridded iron thrusters. And the third is that thanks to the wide open range for the plasma expansion and acceleration, we can achieve significant thrust density and significant scalability with this technology, meaning it's extremely well suited to upscale to high powers, as well as to fulfill the various throttleability needs that are often needed for high power missions. Now in Neutron Star Systems, we are developing a version of the applied field magnetoplasmadynamic thruster, which incorporates superconductors for generating the applied field. We call this combination of technologies supreme, and against other high power options, it stacks up very well. We look here, for example, at two of the most popular solutions for high power currently proposed. These are the VASIMR thruster and the high power Hall effect thruster. Clearly, Supreme has a number of benefits, firstly being the most scalable over a wide range of power classes, anywhere between 1 and 1000 kilowatts, or even up to several megawatts if needed. And the scalability is demonstrated by a comparison of the mass of these thrusters at the 100 kilowatt class. Our thruster would weigh only 70 kilograms here, compared to much higher masses for both the VASIMR and high power Hall effect thruster. We can also consider the fact that we have a wide operating range thanks to the throttleability, a wider choice of propellants, which means that we can integrate with more spacecraft systems. And to be honest, the main disadvantage that is currently facing the technology is the fact that it's at a relatively low TRL and has limited flight heritage. Nonetheless, it offers significant potential for upscaling and inclusion in today's markets, and is certainly worth being researched. So coming now to the various nuclear propulsion and nuclear power programs for space that are being looked at around the world, we start off with the United States, which has often been a leader on this topic. There's a long history of research on nuclear power for space in the USA, well evidenced, for example, by the Prometheus project. This was a preliminary design performed by NASA in the early 2000s, looking at providing a nuclear powered spacecraft for exploration purposes, for example, for the Jupiter Moons mission. At Jupiter, the solar radiation and solar power that is available for solar arrays is significantly reduced, meaning nuclear is a clear option for these applications. They considered what is actually a relatively low power configuration with the 200 kilowatt class reactor, and actually considered combining both Hall effect and gridded iron thrusters for this purpose, whereas MPD could be able to fulfill the purpose of both the Hall effect and the gridded iron thrusters for such a mission. This one wasn't funded, but more recently, under another directive in the last couple of years, NASA developed the Mars 2033 nuclear power concept. Actually, this was entirely intended for human missions to Mars and considered a much higher power class which would be needed in order to reach the thrust requirements for getting to Mars within a reasonable time frame for the astronauts. It's actually considered as much as 10 megawatts in total power provided by two 5 megawatt class nuclear reactors. And for the propulsion system, self-filled MPD thrusters on the order of 2.5 megawatts thruster power class were considered to be able to propel the spacecraft as needed. Another leading nation for the development of nuclear power in space has historically been Russia. Russia, in fact, flew a couple of flight experiments of fission reactors back in the times of the Cold War as part of the USSR, but is also now performing a lot of activities looking to develop these capabilities again. One example is the Transport and Energy Module, otherwise known as the TEM, again looking for various applications, including exploration. And their idea is to use a 1 megawatt class reactor. However, they have a slightly strange thruster setup with a total of 16 gridded iron thrusters of 35 kilowatts each clustered at the ends of these arms. Now, even with these 16 thrusters, this is only accounting for half of the total power capacity of the reactor. So certainly this mission architecture could potentially be improved with the use of MPD thrusters, using a lower number of thrusters at higher power class, increasing both system simplicity and reliability. The TEM laid the groundwork for what is now becoming known as either Zeus or Neutron, depending on the sources that you can find. And this is a spacecraft which is believed to be under significant development at this point, aiming for a number of mission scenarios, even going to the moon with a cargo transfer vehicle capable of bringing 10 tons to the moon, but also for exploration missions like for Venus and for Jupiter. It's a slightly downscaled version of the Transport and Energy Module with only a 500 kilowatt class reactor, most likely to be a stepping stone to larger things and a more achievable near-term target. And based on the available literature, they are looking at using the existing technologies of Hall effect or gridded iron thrusters, which will be fed with xenon gas. Having said that, there are also efforts underway in Russia for developing superconductor-based MPD thrusters, and it is likely that these will be utilized in the future as a more suitable alternative for the electric propulsion for such high-power missions. In Europe, the question of nuclear power in space has always been a little bit complicated due to the fact that, from a political point of view, nuclear power is a questionable topic here. Nonetheless, there have been a number of efforts underway, led primarily in Germany by the DLR, such as the Democritos or Mega-HET project, which looked at a number of different applications for exploration, including, again, trips to Jupiter and also to Venus. And the two projects looked at 200 kilowatt and 1 megawatt class reactors as options for powering these spacecraft. And here they considered gridded iron thrusters and MPD thrusters. The reason for this likely being due to the high specific impulses that could be reached by these technologies, whilst also enabling a high thrust thanks to the power that was available. More recently, the INPPS flagship project has been ongoing, also led by the DLR. And here, this is a European-wide project for developing a conceptual vehicle for various exploration needs. Again, for Mars, but also going to Jupiter moons, in particular Europa. And this one builds on the previous projects of Mega-HET by considering a 1 megawatt class reactor. And in order to take advantage of the international consortium that is present, there are considerations for several electric propulsion technologies to be included here, representing the wide variety of propulsion technologies currently on offer in the European market. Now, in addition to these projects, the UK has recently started looking closely at nuclear power, having awarded a study contract to Rolls-Royce for developing nuclear power options for space as part of a UK Space Agency program. And also, it is pretty much expected that China will also be entering into this topic. Whilst there are no concrete sources available at this time, it is well known that they are developing high power electric propulsion systems with both 150 kilowatt and 500 kilowatt superconducting MPD thrusters already published. And certainly in order to bring these to a commercial realization, the nuclear power will be needed. So coming to the end of the talk, there's a few conclusions which I would like to leave with you and something for you to think about. The first is that high power is a necessity for advanced missions. if we want to be able to get to places with ambitious spacecraft which are far away in both an economic and time-effective manner, then the only way that this can be achieved with current technologies is by using the high efficiency of electric propulsion and enabling high thrust operation with a high power supply. In this case, nuclear power presents a clear option for providing this high power, and in fact there are several forms of nuclear power already possible. In fact, several have already flown in space with the use of RTGs, and they have very good flight heritage, but they are only suitable for fairly low power applications. On the other side, we have fission reactors, which are widely matured on Earth, but we still have the challenge of downscaling them to space applications and launching them safely. And eventually, fusion reactors will likely be the long-term choice for nuclear power in space. However, they are still immature, underdeveloped also in terrestrial applications, and will take a lot of time before they can be used in space. Now, the provision of this power is only one question that we need to look at, and the other is how it can be utilized in the most efficient and effective way. And here we have the two key technologies of applied field MPD thrusters and high temperature superconductors. Between them, these technologies offer significant benefits on power scalability, allowing upscaling to higher power classes and the efficient usage of this power with minimal mass and volume penalties. In fact, by applying them throughout spacecraft, not only on electric propulsion systems, but on applications like power management or radiation shielding, we can achieve significant mass and volume reductions throughout the spacecraft. Perhaps most importantly, the use of superconductors will enable a complete reduction of losses, allowing as maximization of efficiency and therefore the best possible usage of all the power that is being generated. With all this in mind, there's a significant increase in traction on nuclear electric propulsion and nuclear power for space in general. There are currently programs ongoing in the USA, in Russia, in Europe, and almost certainly in China. And especially with the Russians proceeding at a significant rate and leading the race, we could potentially expect the first nuclear-powered space tugs to be launched already within this decade. So I'd like to thank you very much for listening to my presentation. I hope you found it interesting, and this gave you a good overview of some of the various ongoings of nuclear power for space and their relation to Mars. I'd be very happy to discuss further with anyone, and if you would like to find out more, please feel free to get in touch with me.